So at this point, we're successful in analyzing and relating all the outcomes and probabilities in an experiment through its probability distribution. So just as a reminder, if we have a binomial distribution, its graph will look somewhat mound-shaped for a discrete variable, where we have the highest probability somewhere near the center, and then it decreases the farther we go out. And so we know from this distribution that the most likely outcome is somewhere in the middle, and that the distribution is somewhat symmetric, etc. Now, we want to go further and talk about expectation. For example, let's say we have an experiment. This can be any experiment. And we repeat this experiment over and over again for a long time. So we repeat this experiment for lots of trials. So for a large amount of n, where small n is simply trials, our question is, what is the expected outcome from all these trials? So the average expected outcome. So just to make this more concrete, suppose we let x be the number of times a coin lands heads. And then suppose we flip a coin for n equals 100 trials. We already know that the probability of success in this case, this is a binomial variable, it's a binomial random variable, since we're concentrating on the event where we land heads. So we have two events. Our success is landing heads, our failure is landing tails. The event of landing heads has a chance of 1/2, and that means landing tails also has a chance of 1/2, since 1 minus 1/2 is simply a half. And of course this is true for a fair coin. So our success for every single trial is 1/2. So we would suspect, or we would expect that 1/2 of all trials are successes. Therefore, we would expect x in this case to equal 50, or to receive 50 coins landing heads. So in summary, we have an experiment where we flip a coin, a fair coin. We repeat this experiment for n equals 100 trials, and just by intuition or by reasoning, we know that the expected value should be 50. And what we're going to try to do in this video is find a mathematical formula to find the expected value for any experiment. So it turns out that the value of 50 that we found earlier is actually the expected value for the experiment. And this expected value is always the average value of the experiment's associated probability distribution. And we should be more specific because there's multiple types of averages, and in this case we're referring to specifically the mean. And we're considering all the outcomes in the experiment, or all the data points, and so it's a population mean. You'll learn about what that really means in the other part of this course, but for now all you have to know is that the population mean has a symbol of mu. So that's the symbol. It's like a cross between an M and a U. So our expected value, which we can write mathematically or inside an equation as e of x, sometimes you'll see it in square brackets, e of x is equal to mu if we simply have a bunch of samples or a bunch of data points. We would add all of them up. So this is a summation. So this is simply saying add all data points, and then you divide by however many data points you have. But in our case, we're dealing with a probability distribution. So for a probability distribution, certain outcomes are more likely to occur than others. Certain outcomes are more likely than others. And so we're going to weigh them more heavily. And the way we do that is, instead of simply adding all the data points and dividing by the number of data points we have, which is technically weighing them all equally, in this case, our expected value, which is equal to mu, for a probability distribution is equal to the sum of all data points multiplied by their associated probability. So this is the formula that we're going to be using. And this means that if a certain outcome, so if a certain x is really likely to occur, so it has a high probability or a high value for the probability distribution, then it's going to be multiplied by that high value. If this outcome is not really likely, if it's rare, then it's going to have a low value for the probability distribution, and it's going to be multiplied by that low value, and so it's not going to affect the expected value as heavily. So now for an example to demonstrate the concept, suppose we have a 6-sided die and we roll it numerous times and record the number it lands on. We want to know what we would expect the average of all our rolls to be. So in this case, we have an experiment where we roll a 6-sided die and we care about the number that it lands on. So let x be the number that the dice lands on. And we want to know what we'd expect the average of all our rolls to be. That's another way of saying what is the expected value, since it's the average of the entire probability distribution. So in this case, we have a uniform distribution, since every single outcome is equally likely. More specifically, our probability distribution looks like this. We can write it even cleaner. P of x is equal to 1 over 6 when x is equal to anything from 1, 2, 3, 4, 5, and 6. So if x is any of those numbers, the probability is equal to 1 out of 6. So the expected value in this case is equal to the average of this probability distribution, which is equal to the sum of each point multiplied by the associated probability, which is equal to 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6, and so on. Then we can factor out 1 over 6 since we have a uniform distribution. It's common between all data points. So we have 1 over 6 multiplied by 1 plus 2 plus 3, and so on. What we get is 21 over 6, which is equal to 3.5. Therefore, if you rolled your 6-sided die multiple times and recorded the number that it lands on, eventually the average of all the rolls would be very close or approaching the value of 3.5. So another concept we need to discuss when talking about expectation is the idea of variance. So suppose we have two distributions that are continuous, so they're smooth curves. The first one looks something like that, and the second looks somewhat like this. If we calculate the means, or the expected values for both these distributions, since they're symmetrical, it's going to lie somewhere along the middle. In the first case, so this is number 1, this is number 2. In the first distribution, the data points, or all the likely data points, since this continues all the way to infinity, if we consider all the likely data points, so their probability is greater than 0.000 whatever, these guys are more concentrated. They're closer together, so they have a lower spread. And what this means is that I can be more confident that my experimental results, when I actually perform the experiment, are going to line up closer to the calculated expected results. In the second case, the data points of the likely experiments, or likely outcomes rather, are more spread out. So they have high spread. And so I'm less confident in this case that my experimental results will be close to my calculated expected result. And what we can say is that the results, or the data points, or the outcomes in the first experiment are less variable relative to the second experiment. And the way we can quantify this and show it numerically is with variance, and the symbol for variance is var of x. So over here we have a high variance, and over here, or rather, we have a low variance for the first example. We have a low variance, and in the second case we have a high variance. And another symbol you can use in terms of the data points, or what we're calculating, is sigma squared. You guys have actually already encountered the concept of variance, and in fact, if we square the variance, or if we square root the variance, we get sigma. We'll talk about what that is in just a second, but you guys have encountered this concept. For example, when you're performing a chemistry lab or a physics lab and you measure some quantity and you get it to be 5.00 plus or minus 0.01 milliliters, this plus or minus 0.01 milliliters is called an uncertainty, and it's directly associated with the variability of your measuring apparatus. So if your measuring apparatus, if the possible outcomes that it gives out have a high variability, then this uncertainty level would also be high. If it has a low variability, then this uncertainty would be low. And so in all experiments, we try to minimize this variance. Now in terms of calculating the variance, imagine we have our distribution, and we wanted to quantify its spread. So our mean is somewhere over here, and we want to quantify the spread of all the possible outcomes. So if we have an outcome over here, an outcome over here, an outcome over here, an outcome over here, and these are the distances away from the mean, we can quantify the spread, or the variance, as being equal to the average distance of all the data points, or of all outcomes, from the mean outcome. Now our only problem is that outcomes less than the mean are going to have a negative distance, and outcomes greater than the mean are going to have a positive distance. So if we added them directly, then some are going to cancel out and we're not going to get to the result we're looking for. So we can fix this by adding the average absolute distance, and absolute we'll just say means positive. And the way we can do that is we'll say var of x, which is equal to sigma squared, is equal to the sum of x minus mu. So this is going to give us the distance between outcome and the mean. But we want only to add the positive outcomes. So we're going to square this. Since squaring it will give us a positive result, and then we'll divide by all the possible, or the number of outcomes that we have. But once again, some outcomes are more likely than other outcomes, and so for probability distributions specifically, we weigh them just like we did for the expected value. And so in this case, var x, which is equal to sigma squared, is equal to the sum of x minus mu squared for all the data points multiplied by the associated value that the probability distribution has for that outcome. So this is the formula that we're going to be using. Now the only thing here is that we're squaring the value. So you can imagine if we're working with a problem where we're working with, let's say, x has units of dollars. We're looking at the number of dollars or how much money someone has. Then the variance is going to have units of dollars squared. And we can't really mix those two together. Dollars is very different than dollars squared. So what we introduce is a new unit called the standard deviation. And the standard deviation simply square roots the variance. So it's equal to the square root of the variance. So that's the square root of sigma squared, so it's simply equal to sigma. Or another way you can write it is sigma is equal to the square root of the sum of x minus mu squared times p of x. And in fact, when you do measure something in a lab, and you find that it's equal to 5 plus or minus 0.01 milliliters, this plus or minus, or uncertainty, is directly the standard deviation of that device's probability distribution for the outcomes that it gives out. So just an example to wrap up things and make it more concrete. So suppose we have the following distribution, the one in green. We want to find its variance and its standard deviation. So if we recall from a few seconds ago, the variance of x is equal to sigma squared, which is equal to the sum of x of all the data points minus the average squared times the probability associated with the data point. So you can see that we're actually going to need the expected value, or mu, to be able to calculate the variance. So we'll do that first. The expected value, or mu, is equal to the sum of each point multiplied with the associated probability. So we'll take the first point, 3, multiply with its probability, 0.1. We'll add the next point, 5, multiply by its probability, so 0.7. And we'll do the same for the remaining points. And if you plug that into your calculator, you should get an answer of 6.3. So if we performed the experiment associated with this distribution multiple times and we tallied all our results, then we should expect an average around 6.3. Now to find the confidence associated with getting this average, we'll calculate the spread of the data using the variance. So the variance, just to write it once more, equal to sigma squared, the sum of each point minus the average, multiplied by the associated probability. So we'll start with the first point, 3 minus the average of 6.3 squared times the probability, so 0.1. Then we go to the second point, 5 minus 6.3 squared times its associated probability, 0.7, plus 10 minus 6.3 squared times 0.15, and finally 20 minus 6.3 squared times 0.05. And if you plug that into your calculator, you'll get an answer of around 13.71 for the variance, or sigma squared. So just as a reminder, if you're dealing with a question that requires units, so if x is some monetary amount or if it's some measurement, then the variance is going to have whatever units you're using squared. To bring it back to standard units or non-squared units, we'll calculate the standard deviation. The standard deviation doesn't really have another symbol that we use. Instead, we'll always use sigma. So sigma is equal to the square root of the variance, which is equal to the square root of sigma squared, or the square root of 13.71. And that turns out to be around 3.702. Therefore, our standard deviation is around 3.7. And that's your final answer for this question.